All right, hello and welcome to our last unit for AP Physics 1 on gravitation. Now we've talked about gravity obviously since pretty much the beginning of the year, but this is going to be a focus on gravity not as it pertains to objects on Earth, but as it pertains to the force of attraction between large objects in space that have lots and lots of mass. Okay, and the reason we save it for the end is because just like rotation was, it's a very good review of some previous topics. To define the force of gravity, we're just going to say that it is an attractive force between objects with mass. Between objects with mass. Now, the force of gravity that you are used to using is very straightforward. Force of gravity for objects on Earth is Fg, force of gravity, equals m times g, mass times acceleration due to gravity. We call this the local gravitational force, okay? It's used when we're talking about Earth, we know we're not talking about anywhere else, or we don't have to use it for Earth. It could be something on the Moon, on Mars, on Jupiter, whatever, but a location with a known acceleration due to gravity, and in other situations like that. Now, we know on Earth that little g, the acceleration due to gravity, the rate at which objects will accelerate if they are in free fall, is 9.81 meters per second squared, but in this class we've been using 10 meters per second squared. And that changes in other locations. But on Earth it's generally about 10 meters per second squared. Remember that that's the acceleration due to gravity it's not just useful for objects in free fall, it's also a useful constant when determining things like potential gravitational energy. It's useful for determining the weight, obviously, of an object. The object doesn't not have to be in free fall. It does not have to be in free fall in order to use this constant, 10 meters per second squared. Hopefully you remember from last year when we talked about gravitation that Newton's universal law of gravitation is g m1 m2 over r squared. Now, here's the difference between these two. This is the first equation we talked about, is the force of gravity between an object and whatever bigger object that it's on, such as Earth. Okay, so when you're using this equation, you are finding the force of gravity between Earth and another object. This equation can be used to find the force of gravity between any two objects. The reason this one has to do with Earth is because g is a specific number based on your location, if you're on Earth or Mars or wherever. This force, or this equation, can be used to find the force of gravity between any two objects, regardless of if one of them is Earth or a planet or moon or whatever. So, for instance, I could find the force of gravity between this pen and this paper. Neither of those objects is the Earth, but they do both have mass, so they are exerting a gravitational influence on each other. M1 and M2 are the masses. You may see this written this year, and I will do this year, as G little m big M. Little m is just the smaller mass, big M is the bigger mass. Usually that means like object and the planet or moon that it's on. R is the distance between the object's centers. G, the big constant, big G here, is the universal gravitational constant. Which has a value of 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. It might have different units on the reference tables, but those are the ones we usually use. But don't get freaked out if there's different units. So these first three examples are straight up review from regions. You should have been able to do this from last year. What would the weight of a 90 kilogram astronaut be on the moon? The lunar mass is 7.35 times 10 to the 22nd kilograms, and its radius is 1.737 times 10 to the 6 meters. Now you might think, okay, weight, that means mg. I don't know what the acceleration due to gravity on the moon is. I can't use Earth's because the astronaut isn't on the Earth. I have their mass, but I don't know what g is. I'm going to use this because I do have both masses and how far apart the objects are. So, Fg equals g m1 m2 over r squared. That's 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. Mass of the first object is 90 kilograms. Second object is the moon, 7.35 times 10 to the 22nd kilograms. And r, the distance between the moon and the person. You might be tempted to say 0, but remember that r is the distance between the centers of each object. The center of the moon is way far away from the center of the person. Matter of fact, if you think about it, if this is the moon and here's the astronaut, The center of the moon is down here, the astronaut's up here. It is 1 moon or lunar radius away. So 1.737 times 10 to the 6th meters squared, that's going to be r. You've got to be good with your scientific notation in the calculator in order to do these. 6.67 times 10 to the negative 11th times 90 times 7.35 times 10 to the 22nd divided by 1.737 E6, square that, equals, we get about 146 newtons. Now let's compare that to Earth. The mass of the astronaut is 90 kilograms, so on Earth they would weigh about 900 newtons. This is about 1/6 of that, so you could be tempted to say that on the moon you have 1/6 of gravity. I don't know why I said tempted, that's correct. There's 1/6 of the gravitational force on you if you go to the moon. Now, if the astronaut was instead orbiting a distance of 1 lunar radius away from the surface, what would their weight be? Here's the moon. Here's the radius. The astronaut was here. Now, they're up here. They're 1 lunar radius away. Now, that obviously means that the distance is twice as much. So you could take this number, double it, and plug it back into this equation. Everything on top stays the same. The bottom gets doubled. I don't know what that is doubled, but you could do it that way and plug everything back in. I think there's an easier way, because what if you mess up making calculations? That wouldn't be good. I think there's an easier way to do this. I say that we use some algebra. I'm going to do FG prime to indicate that something has changed. And I'm going to write G M1 M2 over R prime. And that whole thing is going to get squared. So R prime is our new variable because the distance between the objects changed, and we're squaring that. Now I know that R prime is equal to 2R. So I'm going to make this substitution. G M1 M2 over 2R. That whole thing is getting squared. We are squaring the new distance. The new distance is 2 times the original distance. If I square 2r, I end up with 4r squared. And what I want you to do is to look at this chunk right here. G m1 m2 over r squared, excluding the 4 that is in the denominator. That's exactly the same as this up here, which means it's equal to the original fg. I have an extra 4 in the denominator, which can be written as 1/4 times the original force of gravity. So what I can do is I can plug in 1/4 times the original force of gravity, 146 newtons. Oops, so 146 divided by 4. And we get that the new force of gravity at this location is 1/4 of the original, or 36.5 newtons. Conceptually, a little bit more difficult, but if you can handle what's going on here, there is a smaller potential for mistakes and for typing things in wrong to the calculator. Plus, once you get good at this, it's much quicker to do this than to do this and just recalculate everything over again. Let's move on to one that's a little bit more difficult. A certain planet has a mass of m and a radius of r. If an object of mass little m from that planet is taken and placed on another planet of mass 2m and radius 3r, how much larger is its weight on this new planet than on its original planet? So we're comparing FGs again. Let's start with planet 1. We know that the force of gravity, and I'm going to use the new form of this equation that you'll see on the reference tables. It's G little m big M over r squared. G little m big M over r squared. Now, all of this fits for the first object, okay, for the force of gravity between the object and the first planet. It has a mass of big M. Planet has a radius of r, so actually I'm going to change that to a capital R right there. And it's an object of mass little m. I don't have to do anything else. That's the force of gravity between the object and the first planet. What about the second planet? Well, I'm told, Fg prime, that the second planet has a different mass and a different radius. So I'm going to do this. G little m, that didn't change, m prime over r prime squared. I'm told that the new planet has a mass of 2 times the original, so that's going to be G m 2m, capital M, over 3r, that whole thing squared. Now remember, when you're multiplying numbers together, the order doesn't matter. As long as they're just multiplying numbers together, the order doesn't matter. So if I have G little m times 2 times big M, I can pull that 2 out to the front, so that this is now 2G m big M. 3r squared is going to give me 9r squared. Look what I have right here, g little m big M over r squared. That's the same as the original force of gravity. I still have a 2 on top and a 9 on the bottom. All this has told me is that the new force of gravity is 2/9 the size of the original force of gravity. Okay? Pretty straightforward. Now, all of that are Regents questions. All of those are Regents questions. Let's do one that's a little bit more difficult, that involves something that we haven't really talked about a lot this year, but that you should know from other science courses, and that would be density. How does the weight of the object compare on a third planet that is twice as dense as the original, and the third planet has a radius of r over 3? Well, for this one, we're going to have to somehow compare the density of the first planet, because we need to know the weight of the object on the second planet. So here's what I'm going to do. Back on planet 1, we know that the equation for density is mass divided by volume. And the symbol for density, you may or may not know, is rho. It's kind of a P with a funny looking tail to it. Rho is mass over volume. That's a capital V, not a lowercase v, that's for speed. And if I rearrange this to solve for the mass of the first planet in terms of the density and the volume, I would get this. I would get the mass is equal to rho times V. V is the volume, and a planet would be spherical. So the volume of a sphere is 4/3 pi r cubed. I'm going to move that to the front, and I'm going to write the mass of planet 1 as 4/3 pi times the radius cubed multiplied by the density. You'll see why this is going to be important in just a second. On planet number 3, we are told, first of all, we know that the equation for the mass for planet 3, based on this, must be m prime equals rho double, I'm going to do double prime since this is the third planet, rho double prime v double prime. The mass of planet number 3 must be equal to, let's see, it's twice as dense, so that means twice the original density. And then for the volume, it's going to be 4/3, not rho, 4/3 pi r cubed, but r is r over 3. The new r, I should say. So that's going to be r over 3 cubed. Now, I need to do this math, at least this part right here. So I have 2 times rho, 4/3 pi r cubed. Let's see, what's 3 cubed? 3 times 3 is 9, times 3 again is 27. So I have 4/3 pi r cubed over 27. And I'm going to bring some of this out to the front. Here's what I'm going to do. We're going to bring out the 2 and the over 27 part. What that leaves me with in here is 4/3 pi r cubed times rho. So I've brought the 2 out to the front and the 1 over 27 to the front. What this tells me is that the mass of the second planet, or this third planet, since 4/3 pi r cubed rho is the same as the mass of the first planet, the mass of the third planet is 2 over 27 times the mass of the first planet. Now that's going to be important now when we go to calculate the force of gravity, or the weight of this object on the third planet. G, little m is the same, big M is different, and r is different. I'm going to go down the line. So I end up with G, little m, 2/27 of the original mass over r over 3 squared. So I'm going to bring the 2/27 out to the front. G, little m, big M, over 1/9 r squared. You could do r squared over 9, but I'm just going to choose to write it like that. Now notice that this, again, is the original force of gravity. So Fg double prime is going to be the original Fg multiplied by 2/27 divided by 1/9. If you remember how to divide complex fractions, what we're going to do here is we're going to do 2 over 27 times 9 over 1 times, again, the original FG. 2/9 is 18, over 27 is 18 over 27. 18 over 27 can be simplified down to 2/3. I end up with the answer that the force of gravity between the object and this third planet is 2/3 of the force of gravity between the original planet and the object. Okay? Little complicated there. The reason it got complicated is because the density equation for a sphere gets a little tricky with a lot of variables in here. But all we did was we made substitutions for the new density and the new volume. We had to do a little bit of math. We found the new mass of the planet in terms of the old mass of the planet, which we then plugged into the force of gravity equation, or the weight equation. Okay? All of that, with the exception of the last problem. The last problem is definitely an AP question, but the first three, these are all Regents questions. I want to introduce you to something new now, and that would be determining what the acceleration due to gravity is on other planets without necessarily having to do a lot of calculation. We're going to actually derive the equation to predict what the acceleration due to gravity is on other planets or moons by just knowing features of those planets or moons. All right, what is the acceleration due to gravity near the surface of Mars, which has a radius of 3.39 times 10 to the 6th meters and a mass of 6.41 times 10 to the 23rd kilograms? So what you could do here is you could find the force of gravity between some object that you make up and Mars, and then, so you could use the Gm1m2 equation over r squared equation. You could figure out what the force of gravity is, and then you could use Fg equals mg and divide by the mass of the object, and you get g. That's a lot of calculation, though. It's a lot of calculation for not a lot of gain. I'm going to show you a different way to do it, and it's based on the idea that both we have two different equations for calculating the force of gravity. We have the local equation, Fg equals mg, and we have the universal law of gravitation, G m1 m2. Actually, I'm not going to do m1 m2. I'm going to do little m big M over r squared. Think about it. It makes sense that these must give the same answer. It wouldn't make sense if you had one equation for gravity that gave you one answer and another equation that gave you a different answer. That would not work out. That would be wrong. I'm going to set these equal to each other. G little m big M over r squared equals m times g. Big G is the universal gravitational constant. Little g is the acceleration due to gravity. That's what we're looking for. Little m is the mass of the smaller object. This little m is the mass of the object that is on the planet, so that makes sense. Those are the same thing. Notice that I have them in each side of the equation. I can cancel it out. Big M is the mass of the planet or moon that you're on, or in question 2, that's causing the acceleration due to gravity, and r is the distance between objects. If your object is on the surface of the planet, then that means it would be the radius of the planet. Look what I've got here. I've just solved this equation for the acceleration due to gravity. You should be able to determine the acceleration due to gravity for a particular planet if you know the mass of that planet or moon or whatever, and the radius of that planet or moon or whatever, or at the very least the distance to the center of that planet. I didn't have to do any calculation in order to get this equation. This is a true equation and can be used in other situations. Now, we're going to keep deriving this from first principles. You can't just write this down and go from there. You have to derive it from things from the reference tables each time, but it's very easy to get to. I'm going to plug in my equations, or my values, 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. The mass of Mars is 6.41 times 10 to the 23rd kilograms. And the radius of Mars is 3.39 times 10 to the 6th meters. So again, look, I've got the mass of Mars, the object that I want to know the acceleration due to gravity at the surface of, and I've got the radius, how far it is to the center of that object. I should be able to calculate the acceleration due to gravity on Mars from this. 6.67 e negative 11 times 6.41 e 23 divided by 3.39 e6, square that. Oh, I made a mistake calculating. 6.67, oops, e negative 11 times 6.41 e to the 23rd divided by 3.39 e to the 6th. Square that. There we go. That makes more sense. G is 3.72 meters per second. And that, if you look that up, the acceleration due to gravity on Mars' surface, you would get exactly that. Second question. What's the acceleration due to gravity near the surface of Neptune, which has a mass of 1.02 times 10 to the 26 kilograms and a radius of 2.46 times 10 to the 7th meters? Neptune's a gas giant, doesn't really have a surface, but we could do the same thing. We're not just going to start from this equation, though. I really want you to practice getting to that equation by deriving, starting with equations from the reference tables and doing some math and algebra until you get here. It's really very quick. Fg is equal to mg. Another equation for Fg is g little m big M over r squared. I cancel the masses, and I'm left with this. G equals g big M over r squared. Big G never changes. 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. Mass of Neptune is 1.02 times 10 to the 26th kilograms. R for Neptune is 2.46 times 10 to the 7th meters. That needs to get squared. So you'll notice that when we did this for Mars, we got a lower acceleration due to gravity. That kind of makes sense because Mars has less mass than Earth, and even though it's smaller than Earth, the fact that it has so much less mass means that the G is going to be smaller. Basically, the bigger the mass, the bigger G is, the bigger the radius of the planet, because you're getting farther away from the center of mass, the smaller G is. Okay, there's the top. Divide this by 2.46 times 10 to the 7th squared. I end up with G for Neptune, well, at least at the surface of Neptune, the top of the clouds there, is 11.24 meters per second squared, a little bit bigger than Earth's. Now, the reason it's a little bit bigger than Earth's, it does have a bigger mass. It also has a bigger R, but the mass is so much bigger that it makes up for it. Okay, so you should be kind of not guessing, but kind of reasoning out as you do these calculations what should be happening with the size of G. Okay, you can usually make a pretty good guess. A new planet is discovered with a mass that is 4 times as big as Earth's mass and a radius that is 3 times as big. What is the gravitational field strength? Remember, this is just a fancy phrase for acceleration due to gravity at the planet's surface. We do our derivation again. Fg equals mg. Fg is also equal to g little m big M over r squared. Cancel the m's. We're left with this. G equals g big M over r squared. Okay, this is for Earth. Earth's mass, Earth's radius. What about for the new planet? We're going to have a different value for G. So I'm going to do G prime equals, universal gravitational constant isn't going to change, but the mass is going to change. So that's G prime, and R is going to change as well. So that's R prime. That whole thing's getting squared. M prime, the new mass, is 4 times as big as Earth's mass. So I have G times 4M over, let's see, radius is 3 times as big. 3r squared. I bring the coefficients to the front, 4mg. 3r squared is 9r squared. I don't want mg. It doesn't really matter, but I like to write gm. Gm over r squared is the original acceleration due to gravity. So this new planet has an acceleration due to gravity that is 4/9 of Earth's. Well, since Earth's is approximately 10 meters per second squared, I have that the new acceleration due to gravity on this planet, 4 times 10 divided by 9, is approximately 4.44 meters per second squared. All right, one more quick example. What's the gravitational field strength 3 planetary radii away from this planet's center? There's one radius. Here's another radius. Here's another radius, 3 away. So the distance is tripled, but remember, this planet had a radius that was 3 times as big as Earth's radius. So this original was 3r. Now it's 9r away, 9r, where r is Earth radius, away. So even though the distance is tripled from up here, that's 9 Earth radii, and that's what we're trying to compare, remember. I'm going to do G double prime equals G M double prime R double prime, that whole thing squared. Big G doesn't change. Remember, M double prime, this is just, it's the same mass of the planet. We're just out a little ways from it, so that's 4M. r double prime is 9 Earth radii, so I'm going to do 9r squared. So this is now 4gm over 81 r squared. Gm over r squared is the original g. So this is 4 over 81 times the original g. 4 times 10 meters per second squared over 81. 4 times 10 divided by 81. We end up with new g at this location is 0.494 meters per second squared. So what I want you to notice here is that as we go farther away from the object, the acceleration due to gravity decreases. Okay? The real goal here, the real focus, is that we now have an equation that we can derive very simply to calculate the acceleration due to gravity on a planet without actually knowing, or without actually getting an object to that planet. It is only based on the mass of the planet and the radius of the planet, how far it is to the planet's center. This is one reason, this is something that goes to show us why all objects fall in free fall at the same rate on the same planet. We know that all objects on Earth fall at a rate of 10 meters per second squared, regardless of what the mass of the object is. This is why. It's because the mass cancels out. The only factors that determine the acceleration are the mass of the planet itself and the distance to the planet's center. So that's an interesting result, and we're going to have a lot more of stuff like this where we're deriving these neat equations for things that we want to calculate. I'm going to stop it there. We're going to come back in the next video to talk about gravitational potential energy and orbital mechanics, which is really fun.